with an engineering mind, you won't actually make problem solving your forefront. The solution will come through the toolkit that he has in front of him.
Well, you actually have to know your stuff technically to convince another engineer to buy your stuff. And that's why I think you need to be a creative engineer to sell production lines.
Both a UX designer and an engineer, they're both creatives. You start asking the questions from the customer's point of view or from the user's point of view. You look at the structure of the toilet and how the toilet was constructed. The siphon mechanism, that's been known for thousands of years really. But it took an engineer to put that in a place where it says, oh, this will solve a problem of human waste.
Welcome to the show.
Thank you very much. Thank you for having me.
The last 2 days when I had a conversation with you, you triggered something in me where you said there's a difference between a scientific mind and that of a researcher, and you went on to explain the differences. And in both the descriptions, I thought, well, I'm a marketer, then where do I fit in? And I want to start the conversation there. What do you mean by that, and how does that apply to you personally as an engineer?
So we talked about the difference between an engineering mind and a scientific mind.
Yes.
Right, and how they apply their roles. So with an engineering mind, you work from a set of axioms and components. You put it together to solve a problem, right? And yeah, you could argue that science is also trying to solve problems, but science is more about discovery. How do I discover what the next thing is? Based on that, you're actually asking more questions than you're actually getting answers. And if you think about the scientific mindset in that way, that's what research does. The researcher goes and takes information and researches it to try and find more details about it, and then keeps on researching until more details come through. And therefore, when you don't actually make problem solving your forefront, it's not your top of your game, right? So with an engineer, gets given a problem to solve, and the solution will come through the toolkit that he has in front of him. Meaning, you could use a set of axioms from physics, or we could use a set of components that he has from other industrial processes that have developed it, and then put it together in a unique and creative ways to solve people's problems. There's, if you think about it, the science of water and water flow has been known since the time of Bernoulli, right? But Bernoulli and the guys who came after him didn't actually invent the toilet, which has a similar flow to a siphon, right? That was an engineer who came up with that. So if you look at the structure of the toilet and how the toilet was constructed, the siphon mechanism, that's been known for thousands of years really, if you look at the history. But it took an engineer to put that in a place where it says, oh, this will solve a problem of human waste. See, and that's what the difference between engineering and then a scientific mindset is.
So Malcolm, I'd like to do a little bit of a role play. So assume that I'm a customer.
Yes.
I'm buying a differential assembly line from you. Mm-hmm. Here's the layout that's been put together by the mechanical team, and you're the controls head, and you've got a team of people that are going to actually design the control system for this production line. So what are the key things that you would look out for, and how would you start the whole sort of design process?
Okay, so with a large line like this, it's fairly complex. There's lots of layers to worry about, from electrical to pneumatics to how machines are going to run on what PLCs, and if there is a PLC necessary and so on like that, where the operators are going to stand, along the line, and how they're going to interact with the machine, so human-to-machine interfaces. So the first thing I will try and do is identify individual stations around here. As you can see, mechanical design has identified individual physical stations.
Yep.
And we have a terminology in our mind. It's not actually set in stone, but it's usually, for practical reasons, we would say an operator station or an automatic station, or a conveyor area, or those kind of things are unique identifiers that we kind of all agree on, that that's how we want to treat a certain station. So for an operator station, there would usually be an operator working there or more operators depending on the setup, and there would be usually a screen there for the operator to look at. Okay, so but from a basics level, if I start from the level 0, obviously I've got my mechanical layout. That's been decided for me already. I can't really do much about it. But now I want to go and add on electronics, right? So specifically electronics, because they will be included, PLCs will be included in that, switchgear will be included in that, safety will be included in that, and anything to do with pneumatic control, for instance. So what I would assign someone to do is go and figure out how much air is this thing consuming from various parts of the line. So we can find out what the best drops are, because if you're going to be consuming more air on this side of the line towards this side, you might have a production line that's going to be starved.
Drop points for air in a manufacturing assembly line are specific outlets where air is directed for various purposes. They include supplying compressed air to pneumatic tools, releasing air blasts for cleaning, cooling equipment, drying components, and providing ventilation and exhaust.
Right, so then if you don't have that flexibility of having multiple drops or even deciding where your air line is going to be, then you're going to have to oversize your pneumatic input.
So if I understand correctly, what you're saying is obviously if there's maybe more consumption of air on the one side of the line, plan it accordingly.
Exactly.
Because I don't put your drop too far away, and obviously
100%.
Machines.
Because air flows like a river, and if the airflow is starved in one location, you're not going to get enough energy and power to power the machines.
Let me start where the story begins, right? When I met you as an engineer. You told me you're an engineering practitioner. And so then I wanted to bridge the gap. Why are you calling yourself an engineer practitioner as opposed to the engineer? Let's start there.
So in high school, I got bored and I said, okay, let me go find something that makes sense to me. And that's when I went to technical college. So I left grade 10, which is, I don't know, the old school standard 8, I think, whatever it is. And then I started pursuing electronics engineering qualification, or higher level education as they now call it. And I did my N1, 2, and 3, which is basically standard 8, standard 9, standard 10, or grade 10 to 12, with a technical matric qualification. And then that was pretty easy in terms of me being interested. So the type of stuff that they taught you there was like, okay, here's a set of mathematical stuff that you need to solve equations for physics.
Working out the current.
Yeah, physics, like you got engineering science that you have to go through, and engineering science that teach you about stresses and strains, how to calculate vectors and how to calculate speeds and all that kind of stuff with a moving vector and all that kind of stuff. And we had to apply the same mathematics principles that were in mathematics class in here because they were related. Engineering, mathematics, engineering science. And that taught me engineering thinking quite a bit. So I ended up spending more time learning about other things than I did with mathematics. How did mathematics come to be? Why are we using certain symbols? And what is Euler's equation, for instance? And I'm only like 14 years old. So, I mean, it's not that I wanted to learn mathematics. I just wanted to understand why we're using this language to talk, and which is not actually being explained in school. So I got pretty bored. I'll give you a quick example of in my engineering mind. I could start seeing it coming out. Was my dad challenged us to go and collect Coke cans on the street, and when we were working from school, and just collect it so you can take it and recycle it, just as a two-part thing, cleaning up the streets and also making a bit of money, which is not a lot, but it was something. And he gave us that money at the end of the day because we did the work. And one of the things that I decided, one of the things we had to do was literally squash the cans every single time. And that was painful because you would hurt your foot, or something just not be right, or and you would twist your ankle or something because you were using your feet the whole time to squash the can. And so I took out a piece of paper and I just drew this column of wood and a brick that can go down through the column of wood, that I could put the can at the bottom and let the can just let the brick just squash the can. And there was this came out of me. I didn't actually ask anyone to do it. I just looked, how can I make my life easier? And I just put this thing together, and my dad helped me make it. When we got the whole pieces of wood together, and I got the brick, and it worked the first time, right? So put the brick down, squashed the cans, took it, and then now we had a production line, right? Put the can in without hurting our feet. And that for me was the sign that I had an engineering mind, because I was able to solve a problem that I was personally facing with a piece of equipment that I made myself. That's the definition of an engineering mind for me.
So then you didn't end up furthering your studies, quote unquote studies, tertiary education?
I think if I just be careful about what I'm saying at this point, because in 2005, right, 2004, I finished the N3, and I wanted to.
So that's high school, right?
Yeah. So just finished the high school, finished the matriculant level, make sure that I got that, and then I wanted to go do the further education, N4 to N6, which is on the next on the plate. I tried to do N4, and I started changing the way I started doing stuff was more electronics focused, more communications focused, and digital electronics, that kind of stuff, more computer focused. I had some personal issues that I had to deal with in that time when my mom got sick, and it took all of our finances, like really just took everything. And it took a lot of strain on me because I had to, help out now and figure things out and learn how to deal with the stress about it. And I was failing. I just failed maths. I just failed science. I just couldn't keep focus on keeping going forward. And I failed that year, and then I just, or not the year, but that semester, and I just hit like a depression, went downhill, and I wasn't able to cope. Luckily, I had some support people around me that were able to pull me out of that situation, but it does happen to people, and circumstances out of your control, you just crash, and that's what happened to me. And I did come out of that, and then my dad came up to me and said, can't pay for my next semester because he ran out of finances. And I was very distraught. I couldn't believe it. I was like, I wasted a whole semester, right? Didn't finish it, and now I can't pay for the finances anymore. And I just couldn't cope with that difference. I thought I was making progress, and now I'm not making progress, and that difference I couldn't cope with it. So I just kind of stopped and left it. And then I went off to work.
What kind of air pressure would you design the machines to?
Well, the nominal standard for all equipment is 6 bar. That's an IEEE standard. I don't know what the standard number is, but typically 6 bar is your max that you would follow in the automation industry. And why is that? There is some reasoning to it, is that you don't want to go too low to atmospheric pressure because nothing's going to work, and you don't want to go too high because that starts getting into the danger zone of components that need to be over-engineered to be able to function on the production line, because the over-engineering costs money. So 6 bar is kind of like a good medium.
Okay, and the minimum?
The minimum is usually 4.5 to 5 bar.
So you would design the machines to be 4.5, to work between 4.5 and 5?
Right.
Okay.
Besides the unusual requirements of some machines to have flow regulation, which means that you might need to have 2 bar or 3 bar depending on the sensitivity of the machine or the application, the sensitivity of that application. You might have a gripper that you need 3 bar, but that's because you don't want to squeeze it too tight or whatever it is. So then you put in 3 bar in one direction and you put 6 bar in the other direction. Okay. That kind of thing, right? Nice. So those are the kind of pneumatic requirements, and then on top of the pneumatics would be, alongside it, should I say, would be electrical. Electrical distribution is quite tricky because of the different countries that you have to go to. So the USA and Europe will have their own standards. South Africa will have their own standards, and Asia will have their own standards. So each region, should I say, we will need to follow the ratings that are applied there. And when you're applying power to the line, there's usually a main insert or main panel, which in this case would be on this side of the line, which is number 2, and then another one over here on this other line. And the reasoning behind that is you want to be able to break up the power consumption into multiple parts if it's possible. just because of the amount of energy that you're going to be consuming over those wires. You don't have to spend so much money on bigger cables.
Similar to the pneumatics, you want to kind of balance it out.
You want to balance it out. Right?
Okay.
So when you're starting off with these production lines, it's usually a question of, in engineers' minds, like what is my energy consumption? Where is my energy flow? How do I distribute that across the production line? In this complex scenario, there will be a lot of calculation involved in determining the flow of the production line and the flow of the air. So more complicated machines like the NVH or whatever this machine is up here, this might require more electricity, so you would need to then plan ahead to decide, does this thing get its own power, own distribution?
Okay.
Do you think the let's call it passion was as a consequence of your external, which you like isolation, or a consequence of something inside of you that was a coping mechanism because of the external?
It could be very much well be that, yeah.
Which one? Both?
The second one, the later one.
Second one.
But also, my personality wasn't tuned to work with people, right? I was very awkward, and I didn't know how to articulate things very well. Even still today, I still struggle to articulate things, but I'm getting better. But when I was 10 years old, if you ask me who are my friends, I'll be like, like could be that guy, it could be this person, but could never really pinpoint to say, yeah, I've got a best friend or I've got some buddies that I can hang out with.
But do 10-year-olds know that kind of information?
Of course they do.
Kind of.
Who's your best friend?
Well, not your best friend, but I think you had friends.
Like
so
my
you had
3-year-old
no friends
knows
at all.
who her
You
friends
knew
are.
who your crew was, right?
My 3-year-old knows who her friends are. She can name them on a,
Yeah, but the comparison is unfair because the 3-year-old you and 3-year-old Ganesh and 3-year-old me is.
But what I'm saying
Different
is
context,
the
different
relation
times.
is still the same. You still feel like, okay, I have people that are interacting with me. Where I couldn't really say that. I could say that only a little bit in high school, where I did have one friend that I made friends with. But that's just because I moved from another town, from Johannesburg down to Mossel Bay. When moving down from Johannesburg to Mossel Bay, it was a lot freer environment. I was able to at least talk to some people and leaving my awkwardness behind, and so I started making plans to see if I can jump ship, meaning I'd leave my town, go to find an engineering job somewhere. And people were telling me Port Elizabeth was quite good. It's nice weather, smaller town, not so hectic like Cape Town. Lots of automotive sector areas there. And this was before the 2008 financial crash. So everyone is promoting PE like crazy because there was a lot of activity going on here. And so I was like, yeah, okay, let me make a plan. So I started asking for donations. I was attending a church at that time. I explained what I wanted to do, and they helped me out with some donations, and family members to help me out with donations. I managed to buy a bus ticket, and I said, okay, well, this is it. I don't have a job, I don't have a house to stay, but I'm getting on this bus and I'm leaving. I better do it now or I'm not going to do it at all. So I did it, and I just got on the bus. I said, okay, fingers crossed. You just see how far I go. The worst case scenario, I can just get on the bus back, let's go, right? But I didn't even give myself room to think that, right? I just said, the only way I'm going to get through this is if I just look forward, Don't even look back. Don't even have any emotions about your home or anything. Just look forward.
How old are you at this time?
20. And I succeeded because I did have connections in PE. I had some people that were living in PE, and then I phoned them up and I told them my situation. They were very kind to offer me a place to stay for a little bit. Through my tenacity of just walking everywhere around PE, I had no transport, I had no scooter. It's another story on its own. I just walked everywhere, right? So taxi fares were expensive as well. You couldn't even get on the bus because the buses didn't follow the routes that you needed. So I just walked, and then I eventually found myself a job at Spur or at a video store where DVDs were still a thing, right? I eventually found it there. I was there for about a month or two, and then didn't like this. Move on to the next one. Got myself as a job as a waiter. And that was very successful because in the meantime, while I was doing that waitering job, I was also attending a Bible college. So Bible college wasn't your traditional Bible college. Well, I don't know what the traditional Bible college is, but it's mainly, we studied the theory and the philosophy and the theological side of things. But the reason why I went there was for the ministry side. I wanted to change who I am to be more approachable to people, right? So in order to do that, you actually have to work with people. So waitering and ministry allowed me to connect myself to people again. And that's how I was able to get out of this introvert box. And then I gave a Google search, went onto Google search, and I just said robotics training in PE. Funny enough, Genemark was the first one that popped up. So Genemark did have or still do, have a cooker training facility. Back then it was a lot smaller, right? A lot more aggregated into automotive and just doing, general people from automotive sectors coming there and doing training. But you could still apply online for some reason, but you had to phone a number. So I phoned the number. They directed me to Chippy, which is our services, was our services guy.
Still is,
right? And he basically said to me, well, in order for you to do robotics training, we need about 15 people in a room or something like that, and you need to pay 5,000 Rand. That was the starting point of the training, right? And I was like, oh cow, 5,000 Rand is like a lot of money for me. I'm earning bare minimum wage here, and I'm gonna have to figure out how to get 5,000 Rand, and I can't even get a loan because I got no credit record. Like really no credit record. So that was challenging, but I said, I'll do it, because I didn't even have a second thought like, oh, I can't do this. I was like, frick, whatever it takes, I'm going to do it, And then Chippy said, well, why don't we do another option instead? Why don't you come in, let me have a chat with you and see where you fit. And I was like, oh, that's interesting. Okay, let me give it a try. So I made a plan to get down to Genemark, and this time I did have a scooter that was donated to me from my parents. They've managed to buy me one, and I was okay with a scooter, so at least I had some transport. And then when I had my interview with Chippy, it went very overwhelming because it's a completely different engineering field. I've never been in this line of work, and we had two massive production lines at that time, the EA111 and the VW250 lines that were being built, and some of it was on site and some of it was here. The actual machinery was here. And Chippy showed me around the machinery, and I was just like mind blown, like what the? It's like, I can't believe this actually exists, right? And then I saw robots. Chippy brought me took me to a massive robot, and I was like, oh my gosh, this is exactly what I'm looking for. How do I get there? And Chippy says, well, why don't we put you on a training program, like an apprentice thing? And I was like, that's exactly what I was looking for all my time. It's just like, what is exactly what I'm looking for? So
he's discarding the 5,000. He's like, forget the 5,000. Now we are looking at something else.
Yeah, and instead it's like, okay, so I said to Chippy, how much is it going to cost? And he's like, no. What do you mean I was going to cost? No, we will pay you to come and do a weekly internship or whatever it is. So we'll pay you weekly to come do the internship. So I'm like, wow, all my answers are pretty much solved here, right? So wow, this is the dream, right? I'm starting somewhere. And so I jumped onto the opportunity. I didn't leave my job at Spur because the switch over was very hectic. And so I was literally working two jobs, one in the evening or one in the day. I would actually drive out to Uitenhage to go and help in the production line there, learn the engineering stuff, leave at 2:30, get them home, shower, get on a bike, go to work, leave at 11 o'clock at night, wake up at 6 and go to Uitenhage. I did that for 6 to 8 months, just continuously. And eventually I broke.
So obviously the main control voltage is 24 volts DC.
Right.
So how would you manage getting the 24 volts to different places? There's obviously conveyors, there's individual machines. How do you go about doing that?
So alongside the 24 volts is also a need to have 380 volts or whatever it is, depending on the country, and also 220 volts.
The single phase, yeah.
For the single phase. All three of those, they work in tandem with each other. So now we start getting into the realm of electronics, where we need to start doing DC to DC conversion or AC to DC conversion. In this case, converting from 120 volts or 110 volts or 220 volts down to 24 volts. You normally go get standard switches, what they call switches, power supplies, that will do that work for you, and then you put it into the different locations. But where do you decide to put those locations? And that's where we get into the control systems area, right? The realm of where are the control systems laying, and how do we control different areas, and how are we making everything into stages, if you would call it like that. I guess stages is the right word. So the way I would approach this is decide how your stations look like, right? So here I can see there's an operator station here, there's an automatic station here, and these are all labeled by mechanical. So we get dictated out of the box, here's all the stations, we don't adjust anything, but we can go and say, all right, so I need to control machine here, or I need to work with operator there, what equipment I'm going to put there. And we normally follow a term or a philosophy who controls engineering here of distributed control systems. So distributed control systems allows us to isolate stations from each other and allows us to create a programming environment that's easier for individual programmers to work in individual stations. And as well, it allows us to create more complex scenarios very quickly without being dependent on the whole production line. And in this case, we would then start off with assigning a PLC here or a control system kit over here, another kit over there, and another kit. So each section would probably get their own PLC or control system section. And that control system section would include the switchgear, the networking, the air, and maybe some regulation to that air, and then the PLC, which is the control system, logic controller itself, and HMI, which is to integrate with the operator so that the operator can, or the personnel can actually interface with the machine. And then some kind of communication interfacing, which means that now that you've got multiple different PLCs or multiple control system areas, you would actually need to interface directly, either via network or from direct online, which is just wires or I/O, or from some specialized machine-to-machine communication.
Okay. So if I understand correctly, what you're saying is this distributed control concept is, rather than having a big master controller or PLC, you actually have created these islands of control. And how would you get them all to talk together? Because obviously it's one system at the end of the day.
So then you still have a master system that controls the conveyor, right? Because typically having a conveyor split up into multiple PLCs is very difficult to design, right? So the quick and easy way to do it is just stick one PLC to control the conveyor. Okay, and then it handles part tracking, which is a virtual concept where you can track a part through RFIDs or through barcodes or whatever you choose for your identification. And it can also give signals to each individual station to say a part is now in place, an identification has been read, and they can send those signals to the station, which then can react to that. And then the station can then tell the conveyor, oh, I'm done with my process, and the conveyor can let the part go. So we use machine-to-machine communication for that, specifically over whatever control system we design it in. For instance, if we use Siemens technology, we would use Profinet as our controls machine-to-machine communication. If we use Rockwell technology, we would use the Ethernet IP way of doing it.
We'll dive into the communication protocols a little bit later. That's a very interesting topic. From the spanner at VW to where you are now, what is that like?
So I have this like tenacity to be able to want to learn stuff, right? And I've always been interested in electronics, and my only entry point in Genermark into electronics was PLCs, or at least control systems, because you work with it all the time. You weren't building it, or at least not they ended that phase when I arrived at Genimoc. They still had an electronics lab, but it was ending, right? There was not a lot going on there. And so I was like, how do I get into that field? Because I want to build things. I want to actually build things, microcircuits and things that I know that I'm really good at, right? And I know that I'm really good at because I've proven over and over again to myself that I'm good at that stuff. And so I started going to the office. Instead of going to Spur now in the evening, I would have some free time, leave at 2:30 at VW, and go to the office, and I would go and sit and start reading catalogs and manuals and just stuff that I could find in the office, and talk to various people from mechanical and the IT side, right? And then Chippy with services, just connecting with people to try and figure out where do I fit. And eventually I just found myself sitting in the IT department continuously. They call it the IT department then, but nowadays we call it the control systems department. And I remember people asking me the questions like, who are you, where you come from? And I was like, oh, I'm this person, I'm trying to do this, and could you help me figure this out? And eventually, through a lot of like asking and probing, I eventually got myself a laptop. I don't know how, but it just came.
I'll tell you how.
It just arrived. I was like, yeah, I got a laptop. Now I can actually go onto the internet. Because at that time, because my wages and stuff were so low, I didn't even have a PC at home, right? So I didn't have the equipment at home to do this stuff. So I literally was spending my time from 2:30 until 11 at night on things that I thought were tangible so I can work with it. So playing around with electronics or looking at catalogs, looking at different types of equipment, and eventually a laptop arrived. And I was like, yes, now I can actually go and Google something. So that was quite an interesting journey. And then I remember time and time again, I'm sitting on the laptop, and then Yanesh would be coming down the hallway, and he would like be switching off all the lights, and I'll be sitting there like, oh flip, the lights are going off. And then Yanesh is like looking, he's like, he sees me and he's like, what the hell are you doing here? Go home. I was like, that happened so many times. Yeah, that was quite interesting. And then eventually I was like, I don't know who this Yanesh guy is, but he's keep on chasing me out the office, so he must be very important.
Those days we used to lock the building.
Yeah,
Close all the doors.
put the alarm on.
Put the alarm on.
Damn. It's
Yep,
long ago. This is what, 2010,
2009.
11? 9.
And then one day, Yanesh is standing in front of a vending machine, different to the one we have now, but
I was about to say, is this thing been here that long?
no, very different. All the ones that were dysfunctional sometimes. So Yanesh was struggling to get something out of there because it was dysfunctional. And I learned from the guys on the shop floor how to manipulate this machine in such a way to get your things out. So I went up to him and I said, I'll help you. And I manipulated this machine, and then, 2 chocolates or whatever it was, it fell out. And I was like, flip, that's bad. So he took his and he gave me one. And then within that moment, I knew that, damn, I've got 30 seconds or something, of a minute. I don't have any more time. He's on his way out. I need to talk to him, right? So and I pitched who I am. I said, this is what I want to do. I'm trying to do electronics, or at least figure out this field where I'm going into. And I don't know what it is that I said to Yanesh, but I think that might have inspired him to invite me into his office the next day. And Yanesh, we had a little discussion. I can't remember exactly what it was, but he was probing me a lot, like a lot of questions. And then he gave me my first task to go and solve a problem.
What was most interesting to me was the method in which he figured out what the problem was. Lots of people will go and jump to the obvious without really understanding the problem, and that's what I learned from him. It's like, actually, there's a few layers that you need to peel open before you get to the problem. You can't jump to what you think the problem is.
Right.
And then it was like, well, I think there's something there. Because if you can have that principle, then I think you can throw any problem, anything at that principle, and eventually you'll find it. And that's not an experience thing. That's almost like a mindset thing. So we've had a number of, put it this way, we have made a lot of mistakes over the years.
Right.
Especially from this high level planning perspective. Just what are your lessons that you've learned over the years that you would sort of try to impart to a young controls engineer, electrical designer that would be joining the team? What would you say? Don't do this because I've burnt my fingers doing that.
So most of the mistakes we've made has got to do with lack of communication within the team or lack of understanding of what the customer really requires. And the first, I don't have really specific examples, but I do have things that I have imparted to other people already, is that understand the customer scope fully, right? If there's a question in your mind about what something does, it's your job to go find out what that is, right? What's the answer? If you can't find out what this machine does, then the communication between the different departments or different tiers has not translated properly, or you've missed out. So you have to be responsible for what you're doing. Finding out the right information, don't make assumptions. The minute you make assumptions about something and it has to change, it's costly.
Yep.
Okay, so we want to try and reduce that. Then the specifications that the customer gives is always king. Because if I choose, for instance, I want to use factory torque HMIs on this production line, but the customer wanted a comfort panels for Siemens, that's my mistake, right? Because the customer doesn't want to buy that. He wants to buy whatever he wants, right? Or whatever the customer's specification is dictating. So that's very important to follow specifications, because we have had it where the customer has scoped something, but we said, no, this is cheaper because it will make the project go forward, or we've chosen this piece of hardware because of timing and we've ran out of time on trying to develop the project, and later on then we had to go and change it because the customer said, nope, it's not part of our scope. One of the biggest lessons I've had to learn was also, if the customer is dictating every single aspect of it, you are holding to that requirement, even down to the programming level. We've had to go and reprogram entire production lines in the way that the customer is asking for, because what we initially put in there didn't meet their requirements. And that cost us lots of time and money, and years of trying to convince the customer we're doing right with them. So that's not a good place to be. You don't want to be in a place where you're just redoing things because you didn't pay attention the first time. For new controls engineers that are coming in and want to learn how to work with these machines, I'll definitely find someone to shadow. And that's very important for newcomers, because then they can learn the most on the job. A lot of the stuff we're doing here, you don't learn in university very easily. You have to go through a specialized journey in order to learn this stuff. Yeah. And it's easier to actually learn it on the job than it is to learn it through that specialized journey in university. Yeah.
Practical learning as opposed to theoretical.
Right.
And that's where you need a mentor or somebody to shadow, as you spoke about.
Correct. And then if you are fortunate and lucky to find a mentor, stick with that person and learn everything that person has and become better. Because the whole point of mentorship is to become better than the mentor. Yeah, of course.
I wanted to... any more comments on the layout and sort of broader picture, because I want to zoom into one of the machines.
I think the very important aspect on this line that most people just overlook and assume that it's there is safety. Because there's a lot of safety aspects on this line that are either isolated to a specific area, or if you apply safety to the whole aggregate of the line, then it affects the whole line. So designing safety controls and doing your sill levels and all that stuff. Sill levels is your levels of severity for how severe the line is in terms of safety regulations. Then when we talk about safety within the whole production line, are you dividing the production line into zones? Are you dividing it up into a way that, if you press E-stop here on this this side of the line, does it stop this side of the line? Those are discussions you have to see, do I have to break up my safety into zones? Yeah. And that's also a Sure, that requires a bit of experience and skill to do that.
Yeah. I remember one of the lessons that we learned a while ago was that safety planning is not an afterthought.
It's integrated, yeah.
It's part of the whole planning process. As you spec the size of the PLC, you have to spec the safety side. Can't be thought of afterwards. It actually is integrated as part of the process.
Right.
And fortunately or unfortunately, that comes with experience. It's not a thing you think about until you've experienced the mistake. I guess that's engineering, right?
Yeah, and one of the mistakes we had was on our Mercedes-Benz project, where we had smaller machines, much like what this part is, right? But they were way too close to the conveyor, and the operators had to work in a very confined space. But we had very dangerous 60 kilonewton presses inside there. They were running at about 100 millimeters per second. That's pretty fast.
Yeah.
So if the operator came into the light curtain, the time that it took for the Kister press to slow down at a specific point, there is a chance that the operator could crush his finger or get it squashed completely. And that was a problem for the safety regulations. And so we had to redesign some aspects of the machine to accommodate for the constrained space that the operator is working in.
Yep.
And so
that slowed the process down, and so you had cycle time issues, and so
that was the one effect. The other effect was we couldn't even get the machine signed off. It took 6 months for us to actually get that machine signed off before they actually agreed, fine, now we're okay.
Yeah.
Right? And we had to go through negotiations like, right, can I slow down the presses? Could I get the cylinders to move a little slower? And yes, again, that had a knock-on effect with the cycle time of the machine.
Yeah. And that's why safety planning has to be in from the beginning.
100%.
It's not an afterthought.
100%.
Just like rework. But one of the things that I wanted to touch on, Malcolm, was one of the most impressive things, apart from your technical prowess and your problem-solving skills, was your ability to recognize your personality, your own self, if you want.
Right.
And I've watched you grow from the person that you were to evolve and develop from a personality perspective. And your evolution has been amazing, but you have to be so self-aware to be able to do that. Maybe, anybody else that's struggling with, wanting to develop from a person perspective, wanting to understand themselves a little bit better, what would you share with somebody, going through that journey?
Yeah, it's tricky to answer that question nowadays because we have bloatware around us. I call it bloatware because you can't get rid of it. Like social media and people on social media dictating, well, not dictating, but sharing content that may transform you in certain ways, and it's very difficult to leave that arena. And the way I was able to start thinking about my internals was the time that I was feeling that intense depression, that I failed completely. Right, I had to think about who am I really. Who am I internally, right? Am I a wimp? Am I a person that's destined to just go down this path of drunkenness or whatever it is that I'll probably landed up on, of drugs or whatever it is? I was like, no, I don't want to do that. Internally, I didn't want to do that. It's just, even now today, I still have adverse feelings towards those things. So something changed in me at that point where the light bulb just went on. I moved out of that zone of depression and moved into a way of like, okay, how do I better myself every day? And I remember I had a lot of people that were looking out for me at that time, because even though I felt like I was alone, there was a lot of people looking out for me, and I didn't know that, right? And I had a lot of people just coming up to me, encouraging me, giving me kind words. And that's very special. If you can learn to recognize that, it will change you.
We're now standing in front of one of those machines that were on the diff line. Mm-hmm. It's a 4-pillar press. It's actually a servo control press that presses a number of components into differential, like bearings and other things. Maybe just talk us through the main components of the machine, and then we can I'd like to find out from you how you would actually design the control system, and then how you'd actually go about programming it, and your thinking around the logic of that.
So I do see that there's a shuttle system over here, and then there's a pressing system over here, or server system. There is 2 locations for operators to enter into, right? So there must be 2 tooling sections over here. Now tooling is the parts where a component will be sitting on, so that you can actually accurately press. So tooling is extremely important for a system like this, for accuracy and stability. I also see some potential sensor systems over here and here detecting, and over here detecting the part in place, or if there's components in the pressing rams. Identifying components like that just by visually, you can immediately see that there's a lot more nuances than just pressing, right? So you've actually got 2 presses technically that you're working with, but it's using the same tool, right? And by identifying that, you can immediately see that you can't do pressing at the same time. That's number 1. So your process operations is going to dictate, okay, I can do this pressing first, and then I can shuttle over to this pressing, or if it's coming from this angle, you do this pressing and then you do that pressing. So you can't do them both at the same time. So by looking at the machine like that, then you can see, okay, so what control system am I going to put here? Well, I've got some pneumatics at the top. So this is a cylinder shuttling this press over. I've probably got some pneumatics here to do some shifting of the tooling, right? So there's some different types of tooling I'm engaging. And I'm probably going to have some pneumatics at the bottom here to also shift some tooling to do different types of engaging, and that's for different types of variants. I would have a valve bank at the back, probably next to a main panel, and inside the main panel there would be a PLC that will listen for the I/O of this whole system. So in controls engineering, this would be logic programming. This would be known as logic system programming.
Logic programming is a programming paradigm that uses logical rules and facts to solve problems. It is based on formal logic and involves defining relationships and constraints in a program. Logic programming is useful for solving problems with logical relationships and constraints. It offers a concise and abstract approach to problem solving.
Because there's various fields of control engineering, but this is specifically for automation and control and logic programming. So you'll see that there's actually a subsystem inside here alongside the PLC, and this is this controller over here with the servo.
Yep.
This makes it really interesting because you've got 2 systems that have to work together. And this is a very good example of a machine-to-machine communication, because what will happen is this subsystem will be controlled by a PLC, but it'll be connected by an Ethernet cable, and there will be communication that will be transmitted over, not from here, but from the controller to the PLC. This part over here will definitely be an HMI, because you need to be able to interact with the machine and control it from a manual operations point of view, service mode, or automatic. So that leads into the programming side. How do you control this machine? The first thing you need to do is set up the I/O. It's like, how is the I/O attached to the I/O cards? Can you give them labels? This is where you start following a standard. Those labels then translate to either something in the electrical drawing, or it translates to some label that's sitting on the I/O card. From there, with the I/O, you turn them into tags or variable names inside your code, and then those tags you talk to them directly. So from there, you start developing a process or sequence of operations. So there's the process that you follow that dictates how this machine will run within a cycle time limit. You get the sequence of operation specifications from the mechanical design, and in the mechanical design, that chart basically dictates what to do from one step to the next step. That's easy to translate those kind of things into a sequence. Usually we use some kind of flowchart kind of derivative for that in terms of programming, like a graph or sequential function charts. That's the same thing, really. But the very important part is understanding interlocks.
Interlocks are safety mechanisms that prevent certain actions or operations under specific conditions. They ensure safety by restricting access, enforcing proper sequences, detecting motion, enabling emergency stops, and facilitating maintenance procedures. Interlocks contribute to a safer work environment and protect both workers and equipment from potential hazards or errors.
Because you can't do one thing without the other thing. Like, for instance, moving the shuttle press and pressing at the same time would be disastrous, breaking the whole machine. So you have to understand your interlocks, and usually if it's a proficient programmer who does his research, he will come up with an interlock table. So here are all my outputs, here are all my inputs. When I'm moving something in one direction, what interlocks must be on to make sure that that is allowed. When I'm moving something in another direction, what interlocks must be on to make sure that is allowed. That's a fundamental programming thing that you must do, and more experienced programmers usually know how to do that out of their heads. So they will just start there, get an interlock table going, and then from the interlock table, you can then comfortably develop a sequence from there.
Sounds like a lot of planning before you actually even open up code.
Right.
You were involved in setting up our programming or PLC programming standard. I called it Cube.
Mm-hmm.
I think you came up with the name, right?
You came up with
Oh,
the
did
name,
I?
brother, yeah.
Can't remember. I don't know why I came up with Cube.
I don't know.
Can't remember.
We looked at the Rubik's Cube and then we thought, okay, that sounds about right.
Can't remember. It was a long time ago, kind of giving our age away. Maybe the necessity for an automation business like ours to actually come up with a standard, and maybe your motivations in some of the theories in that standard that you were instrumental in coming up with.
Right. I thought about a standard, or we had discussions long before we came up with the standard that we need to standardize. It was just plain and simple that every single project we were doing before we had a standard had a different programmer who was assigned to it, and that programmer had their own nuances and quirkiness of how they want to program, and sometimes just blatantly wrong programming. And so we wanted to try and regulate that, but we didn't know how. We had no previous experience, so there was a couple of attempts to actually do that, and we came up with HMI standards first. So how did the HMIs look? That looked pretty good, but from a coding point of view, things were still chaotic and brash, if I should call it like that. So,
and I guess the other risk is when people left, there were unique people assigned to machines and only they could fix it, right?
yes,
Was one of the big risks that.
And that actually is a big story, because we did have a scenario, I don't know, back in 2014, 2015, where some programmers decided they want to go into better things.
2008.
That was the one, and then the other one was when we had 2015, when we had a lot of projects all on the production line, and then programmers decide, I'm going to go into better things because they got better opportunities, which is fair. But now you're left with this equipment that you have to program, and new junior programmers, that's all you have, and then you're one of 3 senior guys that have to go and teach every single junior programmer how to program, because they're just out of university, and so it just got really messy. Plus, you're still dealing with contractors at the same time, because, well, you don't have enough resources, and you've got lots of machines to program, so you employ other people from outside companies, and they have their own way of doing things, right? So that's just the challenges you have to face. And what the standards try and do is regulate that, so to put some guide rails on what you can and cannot do, or at least what makes sense, right? In the beginning, it doesn't make sense because everything is all new and fresh, but as you go through it and you work through the standards, then you start working with it. It works for you. That's the whole point of the standards. It's supposed to work for you.
So Malcolm, you as you said, you've moved on from the standards, and you've obviously part of the Odin workstation team, and you've been integral in developing this overarching control system that manages the process traceability, work instructions for operators.
Right.
But within that, you were focusing on the integration from the let's call it this higher level system to the machines.
Mm-hmm.
PLCs, etc. And I guess you've spent the last couple of years refining that, making mistakes and refining that. I just wanted to maybe ask a couple of questions about the communication protocols and your experience with them.
Okay.
Maybe just talk about what you've developed over the last couple of years before you get to the latest stuff, what you've tried out, what you haven't tried, and why you are where you are now with regards to your opinion and what you're busy developing from a communications perspective.
How do PLCs communicate to the outside world? Well, there's a couple of theories on on that stack, but there's an I/O level, there's a field bus level, and then there's the machine to MES, what they call a B2M. B2M is the business layer to machine layer, right? Which is what we do for MES and so on like that. And then on top of that, you're going to get an MTM, which is machine to machine communication, which could include actually talking from one machine like this to another machine, or a machine like this to a gateway, or a machine like this to an AI system. That would be machine to machine communication. And it's very broad in its description. So I started learning all of those different types of protocols that you can use, notably MQTT and CoAP and various protocols that you can use over UDP, and it was quite exciting. So that's, when we started working with Odin, we decided, okay, what's the best way to talk to a Siemens PLC? We found a library, we started doing some work on that, and we actually developed a protocol around that, which we call JDX. And that has been our version 1 implementation since 2018, actually.
And why couldn't you use one of the off-the-shelf ones? So there's MQTT, OPC UA, CoAP, as you mentioned. Why did you feel the need to make your own one?
So, contrary to what was believed at the time, like, MQTT was known, but it wasn't widely used. It wasn't like, here's a complete implementation of MQTT on a Siemens PLC. They were there, but it was, okay, so I have
This
to
is
make
like
a choice.
6-7 years ago now, right?
Right, this is 2017, 2018,
Yeah.
right? So MQTT wasn't like, yeah, we're going to use this is the future. Now the story is quite different. But if we look at it from the perspective of where we're sitting, we were at the end of that. MQTT pretty much the very next year became the big thing. So we're a bit late to the game on that front.
Or a bit early.
Or a bit early if you want to look at it from that. You could look at it from that point of view. And then we had no idea what else was there because we wanted to try and solve the problem as quickly as possible. So solving a problem as quickly as possible meant that what's the best way to talk to the PLC? Wow, there's actually thousands of ways, really, if you think about it. But we said, okay, no, let's just look for some library somewhere that allows us to connect directly to the PLC. We opted to find one on GitHub, and we tested it extensively, and it worked. And it did exactly what we wanted to do. And we landed up refining it quite a bit to suit our needs. And then we didn't have to worry about the underlying connection to the PLC. We just had to worry about how we want to send data across. And that's when we started changing focus from what the communication looked like to what our data looks like. Because data is very, very important. It doesn't matter what communication protocol you use, really. You can use OPC UA or MQTT and all those things, and your data models are still going to be pretty much.
No, you're communicating because you're trying to exchange data.
Exactly.
It's about the data.
It's about the data at the end of the day. How you do it is really up to you.
So if I understand correctly, you've taken the best of MQTT, CoAP, and OPC UA and bundled it up into your own communication protocol that you call Odin Data Exchange now.
Yeah.
What's your vision for Odin Data Exchange long term? If you could do something beyond what our current requirements are, what's your vision for it?
So I envision it to be able to use on platforms that could be like a STM32 or ESP32 microcontroller stuff.
Microcontrollers are compressed microcomputers manufactured to control the functions of embedded systems in office machines, robots, home appliances, motor vehicles, and a number of other gadgets.
like an Arduino basically, where you could implement it in C++ or C as a library, and you can then define your transport layer. So maybe you want to talk over serial, the ODEX protocol should be able to do that for you. And with the amount of code we've written, you can actually squash it down to the bare minimum as like maybe 100 bytes buffer, I don't know, whatever your constraints are. But we design it in such a way that it's flexible in that size. You can have multiple connections to an outside source. You don't have to have one channel talking, you can have multiple channels talking. So if you need multiple TCP/IP connections in parallel, you can then send data, the same data over multiple channels, and they will all reassemble themselves on the other side. The thing that might be interesting to see how it's going to pan out is our server side, because when you have a client that's connecting to a server, this is the client-server model. We've designed it in a specific way to ingest data and send data that's not necessarily the same as the client side, because the client has its own state machines and stuff like that. So we have to see how we can build that into a client-server model that can talk to another machine.
Yeah.
Right? Then that's going to be interesting to see how we can do that.
In your experience now that you've finally achieved what you've longed for when you were disadvantaged, unfortunately, what do you hope the next Malcolm learns that you wish you had learned, and do you hope that becomes your legacy or something else?
I hope they learn that they should never give up on themselves, because it's very easy to do that. Right? Even though it's an obvious thing, people don't talk about it. You shouldn't give up on yourself. Just treat yourself kindly. You know what I'm saying? If you treat yourself kindly and don't be so hard, if you fail at something, you failed. That's how you get up. It's how you learn from that. And I've failed many times, many times more than most people should know about. And but I've now learned to get up and learn from it. Don't beat yourself up about it. Teach yourself, but don't beat yourself up. You're not a punching bag, right? That's me.
Hope.